Hey everyone, how are we doing? We should be streaming here. Tiffany, good to see you. Let's get Mubot awake right here. Jumping in. Oh, Mubot, he went full screen. We're gonna have Mubot go away. Mubot, you take over. You teach the class, Mubot. He's gonna wake up here and give out some points.
Points for everybody. Time for Brian to come back.
Mubot's waking up. Tiffany has a question on, do we spend more? Adelaide, good to see you. Mubot's waking back up, so he'll be back here in a second. He's waking up to give out those points. So do people spend more on trip to store A or store B? This is comparing two means. So we're looking at the comparison here of two means. It's chapter 17, two means. Do customers, so Mubot should be awake right now. Mubot should be awake. Where is Mubot? Oh, there we go. I got the chat already over there. Mubot is awake. He'll say hi, everyone. Not that I'm typing it. And let's go grab chapter 17 on the quiz right here. Do people spend more on store A or store B? Getting the quiz loaded up. Little chill music right here. And store A, store B, almost there. 100 points in the chat. Chilling out. Store A, store B. This is the comparison of two means. Two means. Here we go. Do customers spend more going to store A or store B? Let's go check it out here. Chapter 17. Oh my gosh, got Tiny Brian here. Store A or store B, do customers spend more? So it actually gives us the notation. This is how many trips they made to store A, how many trips they made to store B. This is the average spending amount on store A. This is the average spending amount on store B. So the sample mean for store A, sample means for store B, and the standard deviation, which is the variation of what customers spent for store A and store B. They're saying we're going to use an alpha level of 0.05, and it even calculates those degrees of freedom for us. So when we're working this problem right here, we'll probably have to work the notation in a moment, but it's asking, let's see right here, we have the means, the data collected, and I think it's just asking in general, do they spend a different amount? So the null hypothesis would be that there's a what difference between the two means. We have here mean for store A minus mean for store B. The null would be that the difference is equal to what? So the null hypothesis would be that the two means have a difference of what? I don't have the PowerPoints open from yesterday. The null would be that the difference between the two means is a difference of what? That there'd be a what difference between these means right here. If we're looking at the two means, the null hypothesis would be that the null has the equal, and the null for the two means is that the difference is equal to 0. So make sure to have a null hypothesis written out right here. We're going to pick that the difference is equal to 0, and then we only change the sign right here. Great work there, Tiffany, 100 points. We're going to say that the difference is not equal to 0. Now, the t statistic, we have to calculate this one by hand right here. So let's go and calculate the t statistic. 2 seconds. There we go. Calculating that t statistic is going to take a moment. And let's go over here to a Word document and calculate the t statistic. Here we go. The t statistic right here is going to be calculated via the following equation. The equation is, let's go green and go red. Y bar 1 minus y bar 2 over square root s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And right here we have A's and B's, and I think they're doing it A minus B. Let's double check. It is A minus B. Good. So they're doing A minus B, and so we can just call this first one here A1 and store 1, store 2, just to make it more sense right there, using the notation that we generally use. So it's just we're subtracting the two sample means, looking at the difference. Then we are comparing, or we're standardizing it by the standard error right there on the bottom. So let's go ahead and plug in our numbers right here to solve the equation. The difference between the two means is going to be 1, 82 minus, we'll put it over here, 82 minus 81. That is equal to 1. I'm going to disappear from the screen. And then the bottom of the equation is the longer part. Ooh, it's going to be a lot of fun solving this. So that's going to be square root of, and then we have the standard, oh my gosh, I chose the wrong means. That's the sample size. Oof, that was almost a big error. 40 minus 53. Those are the sample means. And that's negative 13. So the difference between the means was negative 13. The top of the equation is this right here. I chose the sample sizes. We want the means, the differences between the means analyzed. So now on the bottom, we have to do the standard deviation 21 squared, we're not doing that in our head, over 40 plus 50, 18, there's the standard deviation for the second one, over 53. So we have our notation written, and now let's solve it. The bottom, the standard error right here, we go 21 square it. Oops, we got a whole bunch of craziness going on. Let's go out of the scientific. 21 squared is 441 divided by 40. That's 11.025 right there. Why 40? Oh my gosh. Oh my gosh, Tiffany, you're right. Tiffany, 100 points. Oh my gosh. I should sleep more. Tiffany, wow. Holy mackerel, what's happening, Tiffany? Why? I'm just seeing if people are catching all these errors. Tiffany is totally right. I'm using the wrong values in the equation. Tiffany, thank you so much. Philanthropy question, you bet. Ashling, you got it. Brian's going to get his questions right here. 21 squared divided by 82, which is the sample size for store 1, is that. 18 squared divided by 81 is this right here. Really? 18 squared divided by 81. Well, I'll be. And then we are going to square root this, which turns out to be very close to 3. So it's 3.06. That's what we get right here, 3.06. That right there is the standard error, and this will solve for the t statistic now. So negative 13 divided by this. We're just going to we're going to carry all our decimals, and we're going to do 13 negative divided by this right here, negative 4.25. Double check your work. Very easy to carry a wrong number. Does this make sense, Tiffany, right here as we show the work? Can you do the nonprofit question? You bet. Yeah, definitely, Taylor. Definitely. How's the work look right here, Tiffany? Thank you for catching my errors. I put in the wrong sample sizes. It's all about that notation, right? Put in a wrong number, and then the equation goes haywire. I think we've done it. That is the t statistic right here. So that is the t statistic, and the p-value is going to be basically 0. It's going to be basically 0. So this should be the correct t statistic, which is the test statistic. And the test statistic, there's all of our work from earlier today. And let's go grab our test statistic right here, copy it in. We want the test statistic to 2 decimals. And the p-value should be basically 0. It tells us a t. That sounds about right, Tiffany. Your t will probably also be basically 0 also, because the t statistic right here is calculated, or the p-value is calculated from the t-applet. It told us the degrees of freedom. This degrees of freedom is a complicated formula, which we will not do by hand. And so the degrees of freedom here are 157.87 and 157.87. That's the t we're using. And we could round it up because it won't let us enter that last decimal. And then we put in the t, and the t is 0. The t is basically 0. We should be good on the decimals, but the t is basically 0. And we're good. Now, since the p-value is low here, which one will we pick, A, B, C, or D? Now, this is one we should all know, even if you haven't done this chapter yet. The p-value here is low, so we should be able to narrow this down. The p-value is lower than alpha. A, B, C, or D. This one is one where you get to and you say, my p-value is low. It's extremely small. P-value here of 0. Yours should also be 0. We could go over that a little bit later, Jillian. We've got it in 2 videos. We did it yesterday, and I think we did it the week on Friday, and then I've got the playlist. So if you, in a little bit, we could do that. But check out yesterday's video. We did interpretations, and then we also have, so we could, I know there's a big homework. Yeah. Tell me if you're stuck on something. Let me know. And so what will we do right here? A, B, C, or D? The p-value is low, but let me know, Jillian, if you're stuck. And they'll be like, yes, let's do more. A, B, C, or D? Which one of these? Since the p-value is low, we what the null. Since the p-value is low, so would it be A, B, C, or D? Since the p-value is low, we'd what the null. Since the p-value is low, we'd what the null. The p-value here is very low, so we'd what the null. If the p-value is lower than alpha, the p-value, right, there's alpha, the point at which we reject. We rejected Virginia, great job, 100 points right there. We reject the null, and that means there is evidence for the alternative. So your p-value is that for the p-value. Mine says the p. Yep, so make sure to enter that in. Make sure to enter in. It says to 3 decimals. So Tiffany, yours, I think let's double check your p-value here. You said your t statistic was, I got negative 4.32, and it's giving you a p-value? I'm going to do some checking right here. QT, p degrees of freedom. And was it like 159? NAN's produced. No. QT works how again? I'm doing a check on mine. Oh, okay, no, we want PT. And it looks like, and then we multiply this by 2. And let's do options, SciPen. I'm going a much more complicated way. It's not SciPen? What are you doing, computer? Options. Haha. There we go. So that, I believe, is my p-value right there. I think yours is going to be 0. My t, I don't think your p-value is that, Tiffany. I think your p-value is smaller because what are your degrees of freedom? I'm calculating it right here using a more exact calculator for it than the applets. I don't think your p-value is 0.002. I think it's much smaller than that. You'd have to send me the picture because if you put it into this applet, you should be getting, if you put in, hello, Adetto, good to see you. If you put this in, the p-value there is 0, and we're doing the two-tailed test. I think we're doing the two-tailed. Let me double check. We are doing the two-tailed test. And so the p-values are looking like 0. Double check, because I'm getting p-values of 0, Tiffany. I'm getting p-values of 0 for what we're finding, or basically 0. Down to 3 decimals, I'm getting p-values of 0. Does that make sense? So the applet right here for yours and mine is showing a p-value of 0. Make sure to the right. You might not have entered in the right degree of freedom. You might have like 10 degrees of freedom. Did you change the degrees of freedom, Tiffany? What do your degrees of freedom say? Because you have to make sure whenever you do the T, you always enter in the degrees of freedom. The degrees of freedom are 157.9. So whenever you do the T, you have to go here and enter in the degrees of freedom, and that will change it. So make sure your degrees of freedom are entered in, because then, there we go. Good catch. So the degrees of freedom changes it, and that's which T you are using. You are using a T with 157.9 degrees of freedom, and that's how I'm calculating it over here. It's 157.9. So this would be your exact p-value down to multiple decimal places, just using a calculator that can go more fine decimal place calculations than what the applet shows. But still, down to 3 decimals, this is 1, 2, 3 right there. It's 0 still. And mine was very similar. Mine was like 2.5. And mine is going to be still 0 also. Mine's a little bit bigger, but still basically 0. And that's why we're getting the 0 for the calculation of the p-value. P-value is basically 0, and we reject the null. There is evidence for the alternative, and we got that 100. Yes! Great stuff right there. Good catch. Excellent work, Tiffany. We got the next question coming up. So once again, we would reject the null there because the p-value is low. When the p-value is low, reject the null. We have evidence for the alternative. Philanthropy question. Let's do the philanthropy. You got it. Philanthropy question, chapter 15. And so the biggest thing here is practice, practice, practice. Because we want to be able to solve these questions and know the notation. The better we know the notation, the easier all these questions become. So when you see a question, you see notation on it, be like, what do I need to isolate from this? What is there notation-wise from this question? Let's see right here. Philanthropy question. Writing out the notation. Here we go. Philanthropic organization. Let's go check this out. Philanthropy question. Here we go. Okay, I need your help on the notation. Need your help on the notation. I'm going to write the equation. You start identifying the notation. So this question right here is whether people donate or they don't donate to a philanthropic organization. So can you identify the notation for this? Previous campaigns had a response rate of 5%. We sent out 100,000 mailers, and from those 100,000 mailers, 4,810 people donated. So staff members worry that the rate is lower for this campaign. So I think that's what they're worried about. They're trying to see, yeah, definitely. We can do that one here coming up, Tiffany, you bet. So they are looking to see if the rate has been lowered. So let's do this in order right here. The first thing we do is we actually test out, we write our null and alternative. Step 1 is to write your null and alternative. So when we do this, we need to know the null proportion. What is the null proportion, which is what we assume things are if nothing has changed? Like, it might be nothing has changed, but it's like a starting assumption. What is our starting assumption right here that the proportion of people who would donate is equal to what? So what would we assume if like nothing has changed? What is our null hypothesis right here that the true proportion of people who donate would be equal to what? So knowing the notation is key right here. We've got this. That's something in notation. Got this. The lower is going to indicate something to us. And this right here indicates something. So what is our starting out current belief right here? Like our starting out current belief right now is if nothing has changed, then the true proportion of people who donate would be equal to what? So what would be our starting belief? The null hypothesis states that the true proportion, and we always put the equal sign, the null has the equal sign, would be equal to the null proportion, which is this right here. And we can solve for Q naught. Q naught is the complement of the null. So the true proportion is equal to the hypothesized proportion. We hypothesize that it hasn't changed, so it's maybe still 5%. But they're looking for evidence, and the alternative is the evidence-based claim that the true proportion is less than 5%. That's where the portion right here, has it been lower, is going to come to play when we talk about the alternative. So now we need to write our equation, which is going to be p hat minus p naught over p naught q naught over n square root. And we need to identify the last bits right here because this is x, the number of successes, and this is n, the number of trials. X over n equals p hat. So x over n is 4,810 over 100,000. And these are nice, neat numbers. So p hat. So p hat is equal to, it's the sample proportion. So out of a sample of 100,000 people, 4,810 donated. So the proportion of the sample who donated is 4.8% or 4.81%. And we have that right there. And let's go ahead and bring this over and solve this and make sure to drop some more questions. We got a few more questions lined up, but drop those questions in the chat if you have them. And let's go look at p hat 0.04810 minus p naught, which is 0.05 over 0.05 times 0.95 over 100,000. Ooh, it's going to be decimals. And square root. And that equals this right here. So let's go solve it. And let's go check it out. 0.05 times 0.95 divided by, there we go, square root. And that is 0.00068,202. So minus, and then 0.000689202. And there we go. There's the z-score. Now that we have the z-score, we can get the p-value, negative 2.757. But here's the interesting thing. We can draw this out. Our graph for this, and this is what you want to do. You want to take a moment here and draw out your normal curve. I think so few people do this. Don't worry. I probably wouldn't do it if I was in class also. Good to see you here, Taylor. Definitely. The twin bursts? Yeah. I think I got one where none of the conditions are met, but there's a way you can do the problem where the conditions aren't met. So generally we wouldn't do it, but you should, I think the twin burst one, the conditions are met, Taylor. So I think the conditions are met, but it's like, are these randomly selected? Which condition are you worried about? The success failure? If there was at least 10 successes, at least 10 failures, but make sure you're doing it to the null proportion. So you'd want to use p naught, not p hat. Because maybe they said there was like 8 twins born, but you would use the null proportion. Does that make sense, Taylor? You wouldn't use X. If it says like there was 8 twins born, you wouldn't use that. Which condition were you worried about? You'd use NP naught to check the success failure, not NP hat. That's usually where an error is made too, is when we do testing, we use NP naught to check the condition. And we're going to estimate this p-value here. So we want red. We got our Christmas colors. And the p-value is going to be this right here. It's going to be less than that help. Oh, yeah, no, awesome right there. Great job, Taylor. Thank you, Taylor. 100 points. Thanks for jumping in, just asking a question. That's the way we do it right here. Jump in, ask a question, let me know. This is going to be less than 0.5%. The p-value I can estimate is going to be less than 0.005 because of some numbers I know. I know some numbers. And so I'm going to estimate the p to be about 0.0003. So my guess of the p-value, Brian's guess right here of the p-value, is about 0.003. That's my guess of the p-value. It's just a guess of the p-value over there. But you would probably know across from here is 0.0015. So it's kind of close to where that's at. Let's go look at the exact p-value right here and find out the exact p-value for this question. And we're going to go to the David M. Lane to find the p-value. It looks like we are going to reject the null. That's my guess, 0.003. And we're going over here to Mr. David M. Lane's applet. Bring over to the main screen. And we need to go to the below because we're shading to the left of it. And we're going to drop it in and point. Oh, we were so close. So close. Look at all those decimals. Be right back. You ever have to sneeze and then you don't sneeze? It's like, doesn't happen. 0.003. 0.003. So very, very close guess right there. Probably close enough with the rounding of decimals. And so we did a less than test. Remember, the null has the equal sign. Is the randomization met? We randomly selected less than 10% of the population, random and independent. Success, failure. Do you think... So it literally just does the whole test right here. I think there's other versions that maybe have you do everything, but the p-value here is low enough to conclude the dropout rate would be lower than the previous campaign. So this is the dropout rate. The p-value here is low enough to conclude, so we do have evidence. Just in my example, we do have evidence because the p-value here at the 0.05 alpha would be rejecting the null, and there's my p-value. My guess was close enough to 0.00029, and that's a very low p-value. That means we have evidence that the dropout rate is lower, and we should be good right here. We got it. Great stuff. Good stuff. Let's hop back to the next question. Here we go. The next question is, let's double check. Non-profit company right here. Non-profit company. Non-profit, I think Tiffany's next. As a p-value, so that would be, yep. If that's your p-value, was your z-score something like 4.55? What was your z-score, Ashling? Ashling, was it like negative 4.5, -5 or something like that? I would say your z-scores were like negative something. Yeah, I guess that would do that, right? Yeah, that would be. Almost a little bit higher. Yeah. Yep, so that's low enough. Yep, as long as your z-score is accurate right there, that would be. So that's a very, very small, very unlikely. It's more extreme than mine. That's why I said a bigger z-score. Great job, Ashling. 100 points. Great. Keep up the great work. Awesome. The next question was in organization monitors, was it? I just said it a second ago. Non-profit company. I found it. Here we go, non-profit company. Let's do this. Keep asking those questions. We got like one more lined up. I think we got Twin Burst, maybe. Let's do the non-profit question. And then Tiffany has one too on the research. Let's do this. So a non-profit company is concerned about school dropout rates. And we have right here all the data. Timothy, great to see you here. Ask any question you have, and we'll start working on that problem next. So once again, what do? We mark our notation. Mark the notation. So we mark the notation to start out, and let's do all the steps. So we're basically going to do the steps. We're not going to look at the problem really. We're just going to work the problem ourselves. So when we solve this out, there's 4 steps. 1, we mark our notation and we write the null and alternative. First step is to write the null alternative. 2, check the conditions that it's random, less than 10%. Pause. This is categorical data because we're asking dropout rates. So this will be success failure, which is NP0 and Q0 greater than or equal to 10. And then the next step is to do the mechanics to find the z-score. And then finally, we find the p-value. So let's do these step by step by step. Here we go. Step 1, I always mark my notation. And we see that in a sample of, so this is a sample size of this many. We saw this many drop out. And then we would expect from previous years for the dropout rate to be this. So that's the P0. And if P0 is equal to this, then Q0 is the complement, 1 minus it, just 1 minus. So try and do it in my head right here, 0.882. Double check it. Never hurts to double check. 1 minus 0.8118. And there it is right there. That is Q0, which is the complement of the true proportion. And I think we have most everything we need, but let's write that null hypothesis. The general form for the null hypothesis, so this is the first part right here, is to write the null hypothesis states, and we're testing a proportion right here. So we're going to say the true proportion, always we do equals here, is equal to P naught. So we're just going to take P naught right here and plug that in to where P naught is. So we are hypothesizing that the truth is equal to this. And the alternative we have here, we want to see, has it been effective? So if we're asking, has the program been effective, we'd like the true proportion of dropout rates to be less than this. So you might say, well, how do we know it's less than? If this program is effective, it's trying to stop dropouts. So for a program to be effective, and this is the evidence-based claim, the alternative is where we were looking for evidence. Is there evidence that the dropout rate has decreased? They probably should have just wrote that. They probably just should have wrote, is there evidence the dropout rate has decreased? But saying the program has been effective is saying, has the dropout rate dropped? So now we would check our conditions. Check 2 right here is conditions. So we'd to ask, is this a random sample? Did it say random sample? A little worried about that random sample, right? Which also means it's independent. Is it less than 10% of all students? Yeah, I'd say 1,770 students, less than 10% of all students. And are there at least 10 successes, at least 10 failures? Now to check this one, you would need to do NP naught. And so our N is 1770, and we'd need to do NP naught. So we'd expect this many dropouts right there, which is actually higher than we saw in the sample. And then we'd need to do NQ naught. So N right here is this, and Q naught is this, and that is greater than 10 also. So both those pass the success failure, which means we have at least 10 successes, at least 10 failures, and we're good on our conditions. So we pass the random 10% and success failure condition, and it's success failure because it's categorical data. The next step when solving a problem like this is to do the statistical test. And the statistical test for this one will be P hat minus P naught over P naught Q naught over N square root. And the top part of that equation is just a difference. So it's a difference where we're just asking, well, how far are these two numbers away? So let's go ahead and solve that. Well, we need to solve P hat, which is X over N. So X over N equals P hat. And there's X and there's N right here respectively. And so we have number of successes over a number of trials, and it's 9.4915. There we go. So that's the number of successes over the number of trials, and let's just drop these numbers in. 94915 minus, and 0.118. There's P naught, and then we'll put in P naught right here, times Q naught, and then over N, which is the sample size. And there we go. And the z-score for this is all going to be, this is a standardized way of looking at the difference, because how far are those numbers away? Well, we need context. We need to know, based on a sample size, this difference right here. There's the standard deviation, excuse me. And now let's take the difference between the two numbers. We're just solving the top part of the equation. And then let's divide by the standard deviation. And it's a z-score of 3, basically. Wow. Negative 3.01. And this is awesome, because when we find the p-value now, we can very easily decide what's going on right here. The p-value right here is going to be very easy to deduce, because we're almost exactly at 3 standard deviations. So we know within 3 standard deviations is 99.7% of the curve, meaning outside of this is 0.15%, and below here is 0.15%. Once again, people often say, well, on a test, how could we be asked this? If we land right there, the p-value has to be very close to, rounding to 3 decimals is going to be about 0. We'll write in a different color. The p-value right there is going to be about 0.001. Remember, that is a percent. So as a percent or as a decimal, we would change the way it's written. So once again, we can use the David M. Blaine if we're doing the homework, but it should be very clear when you draw this out that that's a very tiny p-value. It's less than 0.15%. So there it is as a decimal, and yeah. So very, 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 very small. And we've done probably all the work for this. Remember, the null has the equal sign, so any one of these with an equal sign could be correct. We're wanting to see if it has decreased from what it previously was. Compute the test statistic. We computed that, which is the z-score for this. The test statistic is the standardized metric by which we can look at it. And so there's the test statistic to 2 decimals. The p-value to 4 decimals. Ooh. I say it's going to be this right here. Okay, you were a chapter 14 quiz? Definitely. Which one are you wondering about, Laura? Thank you, Laura, for swinging by. Which one are you wondering about? Say, hey, Brian, the philanthropy question, the this question, the birth rate question, the dropout rate question, any sort of question, be like, can you go over this question right here? And we're going to go look at the David M. Lane to get an exact calculation on this. I want to make sure, 1,000 chip trial, you bet, Laura. We got that question coming up here in a moment. I think we have one question before that, but we will do the 1,000 chip trial. 1,000 chips. And whoa, 0.0013. So I think we got it down to decimal place. Oh, we were close. Okay. So now our p-value here is very, very low. The school's observed dropout rate would be, let's see right here. Would be highly unusual. Good. The p-value here is how unusual it is. I thought it said would be high. Would be highly unusual if the national dropout rate was this. Conclude that the tutoring program has been effective. Yes. So we have evidence the tutoring program has been effective because the difference we observe is unlikely by random chance. The p-value right here is the probability of us seeing this difference, which we saw between the two, by random chance. So it looks to me that we have strong evidence that this tutoring program with the dropout rate of 9.49% has really helped out. The original dropout rate was close to 12%, and it's lower now by only about 2%, but that's a pretty decent drop compared to what it was, and it does look to be unlikely by random chance. Yeah, an organization monitors many aspects. Yeah, I think we did that one earlier, but we will go back and we can do it all. We're doing lots of quizzes today, so we will do that. We might have just done it a little while ago. Is 0.019 low p-value at the 0.05 standard? As long as it doesn't give a different alpha level, use 0.05, and you would reject the null. Ashling, great question right there. 0.019 is low, so reject the null. How'd we do? Woo! We're on a streak. We haven't gotten anything wrong in a while. Sometimes I get a little scared, like misread a question. Tiffany saved us from a few questions. Brian was putting in numbers wrong, and Tiffany's like, wait. You put in the wrong standard deviation. Let's go check it out. Next question coming right up here. Everyone's working away on assignments. That's worth 100 points. Thank you, everyone working away. I think Tiffany has the next question right here. Let's see. Tiffany has the next one, then Taylor. Okay. Taylor, do you want me to go over the twin question, Taylor? I can if you want. Maybe we're just asking a general question about it. But if you're like, hey, can you really do the twin? Can you review the twin question? Can you go over that one? I can do it. We have the question coming up. Water samples. Water samples from the mountain on acid rain. Water samples in acid rain. Hey. It's funny. It's like, I'm like, the weekend. I keep getting one of my p-value and I don't know what's wrong. What is your z-score, Taylor? Tell me your z-score. So while I'm loading this up here, tell me your z-score. And then I'll show you what the graphics should look like. I'll show you in the background here what the graphics should look like. So tell me your z-score and then tell me if you're doing a greater than, less than, or not equal to test. And I'll show you what it should look like. I think we got it right here. Awesome. I think this is the acid rain. Negative 1.20. And is it less than, greater than, or not equal to? Is it less than, greater than, or not equal to? If you get negative 1.2, you can actually plug it into everything here. Like negative 1.2. It's either going to be less than or not equal to, I think. This one you have to put in the positive version. We're not going to use this one, though. We might use the outside if we do the not equal to. So here is your less than p-value. So that would be your less than. Here's your greater than p-value. Let me make it a little bigger so you can see. So there's the less than p-value shading below it. Here's the greater than p-value shading above it. Remember, these two add up to 1. And here's your does not equal, which is double the smaller. So that's just double. You can see right there that 11.5. So if the question was asking you something like, it's the twin rate. If it's the twin question, it's going to be this one. The twin question asks if the birth rates have been different. So that should be your p-value right there. Does that make sense? Sometimes you have to reload the app maybe, but that should be your p-value right there of the probability of the mothers who are teenagers having a different birth rates of twins It asks like, is the birth rate of mothers who are teenagers different than the mothers who are not? So that should be it right there. It was the nonprofit. Did we just do the nonprofit one? How does the nonprofit one ask again? Is it asking if your null is not equal to, it's this p-value. If your null is decrease, wasn't it a decrease like the nonprofit's monitoring a school or something? And aren't they asking if it's been effective? I think this is the nonprofit because I think they're asking, has the program been effective, right? If it's the nonprofit, then it's asking, I think, has the program been effective? And if the question is, has the program been effective, then it's this. If it's asking about a change, like it does not equals to, it's this. Does that make sense, Taylor? So this would be, has the program been effective? Has it decreased something? So that would be the less than alternative. Like if you chose a less than alternative, it's this one. If you chose the does not equals alternative, it's this one. So what do we got? Whoop, I'm gonna hit the microphone. Let's hop back here. Next question coming up. We're doing two means now, not just one, but two means. You're welcome. Great job, Taylor. Excellent work. Keep it up. 100 points in the chat. That's the way we roll right here. Acid rain, comparing some means. Let's do it right here. Okay. So we got here a researcher is collecting water, and they're taking a look. Which one's this? This is chill music. Let's do it. Researcher collects samples of water from streams in a mountain range to investigate the effects of acid rain. They measured the pH, acidity, water classified, yada, yada, yada. A lower pH means that the water is more acidic. So you're seeing more acid water in this S sample than in the M and the L. A little bit of an outlier there, an outlier there. The plot to the right shows the pH by the stream, the limestone, the mixed, and the shale. Selected parts of software analysis comparing pH of streams with mixed and shale substrates are shown below. So we have here a 2-sample t-test was performed, and the difference between the means was found to be 0.195. The t statistic was 0.15 with 50 degrees of freedom, and we have here a p-value of 0.8814. Tiffany is saying the answer is going to be C right here. So I think we're testing to see if there is a difference. Yeah, well, it has to be C. You don't even have to really question it because the null has the equal sign. If you know the trick, the null has the equal sign, you got it. We're testing the two means right here. We're looking to see if there is a difference. They don't really make it clear, but it has to be this because the null has the equal sign. Pretty easy right there. What conditions would we have? We would have that these are independent random samples. Now, this one has an additional condition that the group means are independent of each other. So this is the fourth condition. We haven't covered this yet. This is chapter 17. The fourth condition is that the two means are independent. That's like if you have group A and group B, the means would not impact each other. Imagine that we have students taking a Kaplan course to study for the GRE, or Brian teaches them for the GRE. Two groups that are completely different. Then you'd have group A and group B. But if you have students who take a Kaplan course and look at their scores before and after, that would be not independent means. We can go into more detail on the conditions right here. It's kind of their own thing. Put conditions on flashcards, but we'll go into more conditions on what does it mean for two groups to have independent means. You just have to ask, like, if I know someone's score before they take a Kaplan test on the GRE, would that give me information on how they'll do after they take a Kaplan test? And the answer is yes. If someone on the GRE is scoring like 700 on the quant before they take a Kaplan course, you would say, well, they're probably going to score higher. Does it matter or not that my numbers are different? Yeah, they will be different. At this point, it won't matter because it looks like we're just looking at conditions right here. Down here, we're going to look at the conclusion drawn from it, which is where the numbers are really going to matter. The nearly normal condition would state that both of these groups follow a normal pattern, and that could be checked via looking at the histograms, goodness of fit test, normal quantile plot, or the large enough n way of checking. So once again, we have the nearly normal condition, which can be checked one of four ways with look at the histogram, normal quantile plot, goodness of fit, or large enough n way of passing the nearly normal. What are the conclusions you should draw? How would we come to a conclusion on this? What should we look at in this output to draw a conclusion right here? How do we come to a conclusion when we run a test? We just ran some tests a moment ago, and where do we look to come to a conclusion? Every time I'm running tests today, where am I finally getting to make my conclusion? How is the conclusion on a test decided? I didn't draw it out here, so that one doesn't show the full work. Where am I going at the very end of this to come to a conclusion? Like I can tell you my conclusion by looking at this. Look at the p-value. This one ended with not rejecting the null right here, where at the very end right here, we had a very small p-value and we rejected the null. So the conclusion is based on the p-value. So let's go look at the p-value. P-value of 0.8814. So will I reject the null or not reject the null? Will I reject the null or not reject the null? So the p-value here is extremely high. And what do we mean by high? We mean higher than 0.05. The p-value here is ridiculously high. So with a crazy high p-value, what do you think we're going to do? Crazy high p-value. Ridiculously high p-value. What do you think we'll do? Crazy high p-value. What do you think we'll do? When the p-value is high, just let the null fly. Oh, your p-value is very small. So that's going to change things up. My p-value is very high. What will I do? So the p-value tells us, do we reject the null or do we not reject the null? A lot of people like to say fail to reject. Once again, if we say I failed to go to the mall, that means you did not go to the mall. So your p-value is whether you reject the null or do not reject the null. And my p-value is high. I'll just let that null fly. I'm going to not reject it. I fail to reject, and there is not evidence. Now, if you reject the null, there is evidence. That's why I like to say I do not reject the null. There is not evidence. Like I failed to go to the mall. I do not go to the mall. So mine has a high p-value. I fail to reject the null. I'm not going to do that. And there's not evidence for the alternative. We don't talk about the alternative like reject or don't reject the alternative. Remember, the p-value is only about the null. You will reject for yours, and then there would be evidence. If you reject the null, it's because there is evidence for the alternative. And if your p-value is very small, then there's strong evidence. Yeah, they're really small evidence. I mean, really small p-value, very strong evidence. The lower the p-value, the more evidence there is for the alternative. I think I just said null by accident. The lower the p-value, the more evidence there is for the alternative. The alternative is the evidence-based claim, and we start out by believing the null till there's evidence to believe otherwise. We did not have evidence here. The p-value here was very high, meaning that the results we saw here were likely by random chance. Let's go back to the main screen. Okay, next question. Here we go. Is it 1,000-chip trial? We might be on 1,000-chip trial. 1,000-chip trial. I think it's 1,000-chip trial time. Twin burst, I think we did. Water samples. We are just rolling through some questions. It is 1,000-chip trial time. 1,000-chip trial. I'm just going to pull my headphones out of my ear. That's probably a good idea. 1,000-chip trial. 1,000. Chapter 15 quiz. 1,000-chip trial. Let's go take a look. Oh, it's chapter 14. It's chapter 14. Chapter 14 quiz. 1,000-chip trial. Let's go take a look. What? Oh my gosh. Apparently it's just wanting to be mean to me today. Chapter 14, 1,000-chip trial. Finding it right now. Here we go. Chapter 14, 1,000-chip trial. Yeah, probably. I bet we can. We can do the twin birth rate. Kayla, great to see you here. Have you done the twin? Yeah, let's do the twin. People want... Yep, we could, and we could go back. Good practice, good practice. Let's just do 1,000-chip trial. Here we go. I hit more music. Here we go. 1,000-chip trial. Let's do this. Okay, for the 1,000-chip trial, we are first given some data right here. Now, the best way to solve this is with jump. Solving this by hand is going to take a lot longer to solve. So once again, we are going to make confidence rolls right here to figure out the true amount of chips in the bag. So let's go ahead and check this out. We're going to take our data right here and go to copy to clipboard. You're welcome, everybody. Oh, everyone's so positive. Love it, love it, love it. Copy to clipboard. It's a probability, Destiny. You got it, Destiny. You got it. I'll give the answer if no one knows it. But it's a probability. It's the probability of our results or results from our stream occurring via random chance variation given the null is true. The probability of our results or results from our stream occurring via random chance variation given that the null is true. I'll show you visually what it is. It's this. It's that thing right there. That's what it's a probability of our results or results from our stream given the null is true. It's a good thing to know. No, but good practice. Good question right there. Let's go over here. We've copied our data. And so we're going to go to File, New, Data Table. File, New, third time's charm. File, New Data Table. File, New Data Table. And with File, New Data Table, we're just going to open a data. Don't click inside of it. Don't click inside of it. And then with the new data table clicked, we're going to just paste this time. I know you might be wondering, well, sometimes we paste with column names, sometimes we don't. This one didn't have column names. If you look at the question, it doesn't have a name here. Sometimes it says like calories or fat or children's cereal, adult cereal. This one doesn't, so we're just going to go to here to edit, paste. When you paste, make sure you don't see the first thing having the number at the top. This is an error. If you've done this, stop, restart. There's an error right here. Don't do this. So let's say no. And we have right here the column of data we're looking at. So with this column of data, we're going to go to Analyze Distribution. With Analyze Distribution right here, we're going to be able to look at the shape of this. Now, it's not quite going to look like what you saw a second ago. Let's double click it and click OK. And we're going to click the top right arrow and click Stack. Now, there's a quick way to solve this. If you look at it, the answer to the question, oh, do we not have it up anymore? There we go. So, yep. Great job, Kayla, right there. Excellent work, Kayla. Good. And I love people helping each other out. Awesome. If you look, it kind of looks like these, but not quite, because the scale here is different. These go from 900 to 1600, and that probably sounds like a better scale, because this is the lowest value, this is the highest value. See, there's the highest. Let's change this 900 to 1600 by 200. You don't have to do this, but it's going to make it look nicer. Let's double click it, and we're going to type 900 to 1600 in unit increments of 200. This is going to make it look a lot more like that, and boom, it doesn't look like it. Amazing. So closer. I thought it would. Really? Oh. I've had that happen before. Well, I'll be. Well, it definitely has that unimodal shape. Today it's saying no. Today it won't make it look like it. There we go. Oh, it's not in units of 50. It's in units of 200? Let me double check. No, it's in units of 100. Well, that's what happens when you can't read the axis. So it's in units of 100, and there you go right there. So that, when you put it in properly, it works every time. But if you don't, you make a mistake. So it does go from about 900 to 1600. So we are able to identify it. And you'll notice these two have the same scale, but this one has the right shape, and that looks very normal. So check the assumptions. The sample size is less than 10% of the population. So we took 10 bags of chips, of chocolate chip cookies. I'd say it's less than 10% of all chocolate chip bags of cookies. So this is only the independents, though. The data is from a random sample, so we can assume independence. It's not asking anything about the 10%. They're just trying to trick you by combining conditions together. Next, we have the shape of the histogram over here. So, yep, looks like that. Evaluate the histogram, and this one's a little bit confusing. Oh, I think we've gotten this one wrong before. So this one is probably my least favorite question we've done in a while. The histogram is roughly unimodal and symmetric. Yeah, this has to be the answer. It's not bimodal, so bimodal no, asymmetric no. So the answer has to be this one. I don't know why it tricked me. The T is based on the normal, so yes, my Pearson, but no. But it is unimodal and symmetric. It has to be this answer. Great job. You're welcome, Destiny 100 points. Thank you for jumping in, asking those questions, and practicing along with us. What's really great about this question right now is that we get the confidence interval here, and we have to just know how to read it, is that we have a confidence interval going from a lower bound of, here, I'll bring it over here, a lower bound of 1,336, or upper bound of 1,336.37, 36.37, so I'd go to 4. And the lower bound, so that's the upper bound of it, and the lower bound is 1174. Oh my gosh, my chair is really creaky. Probably can't go that. Randomness just happens here. And had this chair for about 2 years now, so maybe time for a new chair. Who knows? What does this evidence say about the company? So how did you know? Oh, for this scale right here. Right here, when you're looking at it, it goes from 900 to 1600. Also, the data, it doesn't make sense, because if you look at this one right here, this would have data from 800 to 900. So there's no data, because these are pretty much in order, except for that one. There's no data down here. Does that make sense, Lauren? There's no data. There should be occurrences. There should be a bag of chips with 800 to 900 chips, but that's not how this one looks. There are bags right here with 1,000 to 1,100 chips. That'd be this bag of chips right here. That is the bag of chips that is this block right here we see. We see a lot of occurrences. We see 1, 2, 3, 4 occurrences in this region. So you could also look at the... No, Lauren, thank you. Keep asking those questions, Lauren. Good question right there. We also don't see this shape where we see 4 bags of chips. Or how many is that? 1, 2, 3, 4, 5. 5 bags of chips. So that would be a bimodal distribution where there's 5 bags of chips in this range, which we don't see that. We only see 1 bag of chips. And so if someone were to call and complain, they say, my 1 bag of chips did not have 1,000 chips in it. We'd say, well, we're very sorry, and maybe we'll give them another bag of chocolate chip cookies, because we're not talking about 1 bag of chips here. We're trying to estimate the true mean. Like, I am 95% confident the true mean number of chips in a bag is contained in the interval 1,174 to 1,336.4. I am 95% confident that the true mean, not an individual bag of chips. So because the model is entirely above 1,000, the mean number of chips in a bag is likely more than 1,000. This does not mean every bag will contain at least it, so that's wrong. Because the interval is entirely above 1,000, the mean number of bags of chips, like on average, if people buy our chips, on average, they'll see more than 1,000 chips. But we cannot promise that an individual bag of chips will have 1,000 chips. Like, we can't say, we know every bag will have 1,000 chips. We can just say, on average. It's a great company thing, right? To say, on average, our bags of chips have 1,000 chips in them, on average. Like, if you buy a bunch of bags of chips and you look at on average, you will get at least 1,000 chips. That's what we believe. We don't know that every bag will have at least 1,000 chips because there's variation that we're going to see in each bag of chips. And maybe you'll get like 900 something chips sometimes. Very possible. Good question right here. I really like the end of it. Like, what does it mean that we're interpreting this? This is about on average for all bags of chips. We think the true amount of chips in a bag is somewhere in the interval 1,174 to 1,336.4. We can't promise you for every bag of chips that you'll get 1,000 chips in it, but we think the truth is that we have at least 1,000 chips in our bags on average for the true mean. So let's go check out that next question. Here we go. Great work, everybody. Excellent work. Excellent work. We got twin bursts. We haven't done twin bursts. Oh, we got the microwave one. Let's go check out microwave popcorn question. Microwave popcorn. And then I'm thinking, is there another one? Tell me if I missed it. I'm thinking, is there another one? Got microwave popcorn. Might do some like multiple choice on these. Microwave popcorn. Oh man, we found it perfectly, really quick. I feel like there's another question. An organization, many aspects. You bet. Here we go. And drop more questions in the chat. All right, let's go do some microwave popcorn. Here we go. Suppose an experiment was done to gather data on the number of unpopped kernels. Oh, I don't think we've done the new printer one today. Yeah, we should do new printer. We haven't done that one, so we might do that one next. I don't think we've done that one today. Half of the students in your class took home a bag, put it in the freezer overnight, and popped it the next day. The other half took the bag, left it on their kitchen counter overnight, and popped it the next day. Each group counted the number of unpopped kernels. Could the methods in these chapters? So this chapter is about two means. So think about this. You have two groups. One group is going to count how many unpopped kernels there are in their bag, and the other group is going to count how many unpopped kernels are in their bag. So you'll get the average number of unpopped kernels for group 1, the average number of unpopped kernels for group 2, and with this, we could look at the difference. And that's what this whole chapter is about. I think we have some other problems where we're looking at that. Where did we do some differences between two means? Right here. So you could say, like, this could be the data. We had 82 students, it's a big class, take the bag one home, 81 students take the other bag home. And then there was an average right here for this group of 40 unpopped kernels, an average of 53 for this group with a standard deviation. And this completely applies. This would apply. Now, the reason it also applies is because these are independent means. Like group 1's bag of popcorn and group 2's bag of popcorn, is it going to matter which mean they have? I mean, if their popcorn kernels pop?
It doesn't matter.
You knew what he was going to say. This is to say, like, if group 1 has more unpopped kernels, group 2 will not be impacted by that. The means are independent of each other. So group 1, their popcorn doesn't pop. That does not impact group 2. But if we had like someone do a follow-up, like you re-microwave the bag of popcorn, like you put it in the freezer overnight, you microwave it, and then you microwave it again, Then we'd see a dependent mean, like the microwaving the second time, how many pop the second time would depend on how many pop the first time. So then we would see dependent means, which would violate the rules for this chapter. So this should meet it. This is two independent means right here because we have two groups and we're comparing how many unpopped kernels there are between the groups. So we can see on average which group has more popped kernels. That's the goal, comparing two means. Let's go check it out. Good stuff right here. I'm going to put on this song. I don't think we've done the printer question today, so we'll circle back, Destiny. I think we've done the organization monitors. Jackson, is the printer question chapter 15? We got enough time right here. We'll swing back by and do the organization monitors again, I think. So I try to do as many new questions. I try to do like as many as we can because I know a lot of people. And thank you to anyone who uses these videos later on. It means a lot to me. Like sometimes they get 1,000 views and I'm like, whoa, 1,000 views. So I try to think of as many. How does the printer question start? Found it. Here we go. Time for the printer question, Jackson. Here we go. Get ready for the printer question. Drop those questions in the chat. You bet, Jackson. Thank you so much, Jackson. 100 points. Let's do this. Okay, you ready? You know what we're going to do first. We're going to find that notation. Let's go find that notation. Here we go. Grabbing some notation. Open another Word document because we've got to get all those Word documents open. That's how you win at life. Word documents. And here we are. We have a startup company here with new printers. They're trying to do a campaign to see if they can get some brand recognition. 37% of people currently recognize their brand, like if nothing were to change. And then they poll 423 people after and find that 173 recognize their brand. Kayla is crushing it. Amazing work, Kayla. I just hit the points button immediately. That's the sample size. That's X. And X over N is P hat. So let's go find the sample proportion. And Kayla's already got P naught right here, which is the hypothesized. And if we know the hypothesized, amazing work. Great practice. Oh my gosh. And those are complements of each other. P hat. Kayla, thank you so much. P hat is just X over N. And we're just going to solve it out right here to 408,983. And that is P hat right there. P hat is the sample proportion. And now we just need to solve this. Let's write our null alternative. What is this company looking to do? If you think about brand recognition, you'd like evidence your brand recognition has done what? Yeah, let's do this. We'll do Twin Burst next, Destiny. We haven't done that this afternoon, so Twin Burst is a good one for us to do next. If we're trying to look at our, and then Tiffany, you got yours next. You got it. So if we're trying to do brand recognition, what would we do? We'd want our brand recognition to do what? What would we like our brand recognition to do? Like currently, let's write out our null. Currently, our brand recognition, we would assume is equal to what it has been in the past. We'd like evidence, if we're going to continue this, for our brand, you got it, for our brand recognition to go up. So is there evidence that this campaign has worked? So would you recommend the company continue using this? So they're trying to ask you right here, is there evidence it's gone up? Now it's going to be very important when we find the p-value on which way we shade the curve. And we'll be doing that here in just a little bit. So now we go here and we solve our equation. P hat minus P naught over P naught Q naught over N square root. And now we put in P naught, or P hat, excuse me. If you want to memorize something, just write it 50 times. I've probably written it 5,000 times. Bunch of times. And then you memorize it and you say, I know that equation. And the top is just a difference. Like how far are these numbers apart? And then the bottom just standardizes it to say, well, is this difference we see up top really that large? Because all you're doing right here is finding a z-score, which is how many standard deviations are things away. Ah, yes, Tiffany, you bet. We'll do that here in a little bit. I think we have enough time, 30 more minutes left. And so let's go find this z-score right here. And 0.37, we're solving the bottom first. And we square root. And then we take the top, 0. Gonna mess it up. There's the p hat. I think I saw that it's gonna be a z-score close to 1. Yep. Ooh, we can solve this. Kayla, I bet you can guess, Kayla, 500 points. If anyone, don't use this David M. Lane yet. Take a guess at the p-value of this. It's a tougher one to guess, but I think we can get close. Take a guess. The z-score here is equal to 1.06. So 1.06? Yes, 1.062. We'll put the 2. It might say to 2 decimals. So the p-value is going to look something. Take a guess. Oh, that's too close. Sure. The p-value is going to look something like this. Any guesses of this p-value? We can probably guess. I'll write down my guess. My guess is 0.146. It's my guess. 2. See how close I was. Because I know it's a little bit less than 16%. Little bit less than 16%. How close were we today? So we're going to go here and we're shading above because it's to the right. We're going to copy our z-score. And 4.4. Close. Just off by a few decimals right there. So I said 0.1462 and it's 4.1. Oh, close. But once again, this is why we can take guesses and stuff like that. Oh no, okay, I'll still throw you the 100 points. Don't worry. Just always try to take a guess at what the p-value is going to be using like empirical rule numbers, because we can do things on the test where it's like, well, what do you think this will be close to? You're like me. I've got so many things open. But no, I'm really lucky. Thank you once again to Haslam, College of Business, UT, everything. Like, it's so weird to think like I work online and I just broadcast streams and stuff like that and teach college. Like, who teaches college online? I do. I don't know. It's pretty cool. And I hope everyone's having a great time here. I really love it. It's like, it's just, what are your thoughts? What are your thoughts about Stats 1 online? Well, you see, this is convenience bias to the nth degree. Like this is the absolute. This is the absolute. I know I've got so much of it. Null has the equal sign. We're looking for evidence it increases. Test statistic to 2 decimal places was 1 point. There we go. Like, wow, everyone who shows up likes this. Well, that's because you showed up. There's the p-value we found via the David M. Lane, shading to the right of it. Oh, thank you so much. I like it when people say, thank you so much, Houston, right there. Yeah, and I don't care if you say you don't like stats. That's fine. I don't like English, and someone can make an English class great. I'm not the biggest fan of English. Like, not being like, well, I don't like English. I can see how, like, I would say to someone if I took an English class, I'd be like, I like this English class, even though I'm not a big fan of English. Like, I like English, but I don't know. I've always met English classes. I like logic. I like code. I like logic. I like things where you can deduce things. And English is more like, I don't know, the rules of grammar just, gosh, I hate those. The grammar makes no sense to me. No sense. Thank you so much, Houston, right there. Yeah, you got it, Kayla. You're going to do awesome. And I'll send you some resources over. I'll send you data camp beforehand. If you just do a little bit of work, you'll come in day 1. Kayla, make sure to talk to me about preparing for 320. And I don't want you to like spend your whole Christmas break working. All I want you to do is like download have our studio on your computer, just take a little bit of a look at it and just like see a few things. If you probably put in like 5 hours worth of work over Christmas break on it, like just looking at it here and there and just pulling it up, have it installed, have it ready to go, you'll walk in day 1 and you'll be like, this is the answer to this. This is how you do this. So yeah, Kayla, you got it. I'm going to talk briefly on that in a second right here. Our p-value is higher than the alpha level. Hopefully I haven't made an error on this. Our p-value is higher than the alpha level here, and so we do not reject the null. So would you recommend the company continue to advertise? No, because we don't have evidence. No, because the null is not rejected. There is insufficient evidence that we have helped out. What did I do? Oh my gosh. I think I totally got just because the null is rejected, there is sufficient evidence. Okay, so what did we do? Something went really wrong on my calculations. Wow. Okay, so the calculation here went haywire. Okay. Brian made a calculator error. Wow. Owen Wilson?
Wow.
He knows about that. Okay. What am I doing? I square rooted that, right? Do you see it? my gosh. That's the biggest error I've made in a long time. Do you see it? I went on autopilot. Oh, and it's because of how I marked it. You're welcome, Campbell. Well, apparently I'm not helping. I was gloating like, we haven't made an error in a long time. We haven't made an error in a long time. It's like, put that on loop. I'm so sorry. Solving problems live. It's the way it goes sometimes. It's the way it goes. This drastically changes. Error in the calculation. And apparently it's going to be big enough here that it's going to come out statistically significant. I was like, an error that big that it's saying it is statistically significant. There we go. 1.66. Now we're going to guess the p-value. Oh. So 1.66. That moves the z statistic over here. And now the p-value, we just disappear the whole thing. Oh no, Jackson, did you? Jackson, if you did, Jackson, you're one of my students, right? I'll fix that for you. Jackson, was that one of the questions and you failed it? Jackson, let me fix that for you. No, it was my error. I put in the wrong end. Jackson, did you seriously fail it and submit it and had that issue? I will fix it. Oh, Jackson, you messing with me, man. 100 points. I would went in and fix that for you. You totally had me going. The p-value here I was like, oh, I'm so sorry, man. Sorry, man. Oh, wow, they're really playing games with us. This p-value is going to be, let me look at the z. Look at this. The p-value here is going to be, well, I guess you rejected it anyways. 3 decimals, whatever. We're going to guess it now. Take that. Oh, look at that. We can guess it now. The reason being is this is very close to a z statistic I know. And what we do is we go to the David M. Lane. We are doing the greater than test. And there it is right there. And it does decimal place round to 0.48. So because I know 1.645, which is the 90% confidence interval, I can guess the z-score for this, or the p-value for it. Once again, you don't have to guess these. You can use the applet. The applet's going to solve the right answer for you. But good stuff right there. And wow, if you calculate this wrong, everything goes haywire. We don't like that right here. So we got it right. Let's go back here to the main screen. Quick 2-minute aside right here. So if anyone's taking BAS 320 with me, here's my suggestion to you. This is how in 2 minutes, I can give you advice that 2 minutes on how to get ahead in BAS 320. Here we go. Install R and install R Studio, and then reach out to me about data camp access. So reach out to me about getting access to data camp, which is something we have where you can practice coding for free. And when you look at this right here, this looks intimidating, but this is where I'm going to do my work. This is free. Our studio is free. R is free. And I'll put the playlist in the chat because it's probably the best thing I can do right now. My getting started in R playlist. And so, oh, I've got the playlist pinned on the screen. Getting started in R. I should change the playlist. Oh, I broke it. So here's the Getting Started in R playlist. And R is free. R Studio is free. Yep. And you'll download it in Mac version, PC version. And watch this. This is how you code 2 + 2. There you go. What if we had, so let's do, I'm going to spend, I'm going to spend 2 more minutes, Kayla, on this. But watch this. If I were to collect data on people's heights, I would go here and concatenate a vector. This creates a vector. And so I've opened up a vector and I asked somebody their height and they say, I am 5'10", 70 inches. Now I put a comma for the next observation. And the next person says, I am 5'4". Next person says, I am 6'3". Next person says, I am 6 feet tall. If the next person says that they are 5 feet tall, what will I write next to put the next observation here? So all I'm doing is just storing something called height. That left arrow stores into height. So if someone says, I am 5 feet tall, what do you think I'll write next? Next person says, I'm 5 feet tall. And so we're just going to create something called height that has values inside of it. Yep, and then we'll put a what there. You're right, 60. Great job, Houston and Kayla. But we need to put one more thing. You are correct. We'll write 60, but we'll add a comma right there. We'll add a comma. And so now that is the next observation. That makes sense. And the next person says something like, I'm 5'5". We'll add a comma, and it goes the next observation. So watch this. If you want to take the mean of height, you can take the mean of heights right here, and it's got autocomplete. How about if you want the standard deviation of heights? What do you think we would do if we want the standard deviation of heights? Just put 2 letters here to change it to the standard deviation of the height vector. That's the mean of the height vector. How could we find the standard deviation of it? Pretty quickly. What do you think I could do to find, like, take this vector right here, and this is running a function on it. I want to find the standard deviation. What do you think I could do to the height vector I created to then take the standard deviation of that height vector? So I just have 6 observations. It says it up there. It's in the brain of R. That's where the brain is at. The brain's up here. It knows these heights. It says there's the heights and the values we see. So how could I find the standard deviations of these people's heights? And then I'm going to ask one more question after this. How could I find the standard deviation of these people's heights? Think of 2 letters. Just think of 2 letters. And this is why we don't work these things by hand. Only 2 letters. Only 2 letters. How would I find the standard deviations of people's heights? Only 2 letters. Just think of 2 letters to find standard deviation. Jacob, good to see you here. Only 2 letters. Like, if I do standard deviation, what 2 letters might I use that would be a function that would find standard deviation? Don't worry, go out on a limb. Oh, on Top Chat. I've been on Top Chat this whole time? SD, exactly. Kayla, can you think of any other functions we could run here? Like, if I want to find the lowest value, the highest value, the middle 50%, maybe take a summary of the data, or all these different things. Could you think of any other functions I could write that would then take this data I have, because I have data right here, and I just want to maybe find, the lowest value, the highest value, the quantiles of it. Like, what other functions could you think of right here? Oh, you can find the sum. Oh, yeah, instantly. Yeah, just go right here and just say, find the sum. Great job, Kayla. Another 100 points. There's the sum of it. You know what we could do? We could divide by the length of the vector. And if we divide by the length, which is how many observations are in this, guess what we just found? We just found the mean. You could go right here and just ask for the median of this. There's the median of that vector. You could ask for the min of this vector. There's the min. You could ask for the max of this vector. And all we're changing is just the name of the function. Quantile of this vector, you could go to the unique values in this vector, and there's just all these things you can run right here, just like this. So if you look, we're just changing what we're asking of it. Take this and find the mean of this. Take this and find the median of this. All these different things here are just very simple functions and kind of where we begin. So if you start to understand how this is used and how we made a vector right here with certain values in it, and then we're just asking, what is the mean of this vector? What is the standard deviation of this? And this is just a function that just runs an operation on this. Like, it says, take this object and find the standard deviation of this object. Take this object, find the heights. Harper, great to see you here. But Kayla, hopefully this doesn't seem too intimidating. This is kind of the basics of it. And we'll talk about what this means, like with arguments and functions. And we go through a whole basics of this. And Data Camp has courses on this, but you've probably heard about 20 minutes of the first week of class here. So if you're like, it doesn't look too bad, not too bad, that's all right. So don't worry, but we will go over this, and getting a head start on it will really help. First week you'll be like, psh, I got this. Great stuff. Which questions do we have lined up? Oh, we got 15 minutes. Oh my gosh, time flies. We have the standardized scores. Oh, the next one was the twin bursts, right? We haven't done twin bursts. Okay, twin bursts. We've done a lot of questions during Office Hours Day. All right, twin burst question. Twin bursts. Write the null and alternative hypothesis you would use. We could do that one here next. We're going to probably focus a lot on chapter 15 because that one's due tonight. So let's do the twin birth question here. Twin birth question. I think we have time for like 2 more. Oh, twin birth question. Visualization time. We have, I know you did an Office Hours this morning, but I'm confused on how to make the graph charts. Check out the visualization playlist. So I'm going to put that in the chat also. And I walked through the step-by-steps on how to do the visualizations. And you get to see the Joker. So I'm going to drop this in the chat, and then we're going to do some twin stuff. Viz playlist. And I did the visualizations in another Office Hours too. But check those out right there, Harper. Let me know if you have questions. But there's the visualization. You're welcome, Harper. Thank you so much. And I walked through step-by-step and show the button clicks on how to get the stuff. Let's go check out the twin question. Here we go. In 1996, a national vital statistics report indicated that 2.7% of all births were twins. Is this rate the same? There's the question. Is this rate the same among young mothers? So that's what we're going to be testing. Is it the same or is it not the same? So let's go examine this and see if it's the same. So once again, what do we do right here? Thank you so much, Kayla, right there. We have right here 2.7 is the what it was previously. 7 sets of twin were born to 420 women. And so now we need to mark our notation. The notation here is this is P naught, because that's what we are hypothesizing is true if nothing is different between these young mothers. The complement of this, we do 1 minus to find Q naught. Q naught is 1 minus. And there it is right there. That is Q naught, which is the complement of the true proportion. 0.973. And so this here is the number of successes. So that is X. And don't mix these up, because maybe one time I did. So that is X and that is N. N is the number of trials. X is the number of successes. And we're asking if it's the same. So if these young mothers are like other mothers, well, then the true proportion of their twin births would be equal to what we see for the other mothers. If they are different, then the proportion of twin births that they have would be not equal to what we've seen. P hat, thank you so much. I make some errors, right? X over N is P hat, and P hat right here is 0.111601. Yeah, so that's, oh, I should know what that is. That's not a third right there. That's a 6. So that's, oh, interesting. It's pretty interesting. Interesting numbers, right? So there we go. Yeah, 7 over 420. Boom. Nice job, Kayla. Excellent work. I'm so afraid I'm going to get something wrong now, Kayla. It wasn't your fault. It was totally mine. I'm just like, I don't want to get 2 questions wrong in a row. I'm just like, so right here, we have P hat is equal to point. I'm like, I can't get 2 questions wrong. I can't in office hours say getting 2 questions wrong. When that 25... if my fiance, if I ever double check something, I'm like, I swear. Well, you need to double check my math, especially after that last question. We went all these problems right here without getting something wrong, and then got a 25. And I was just, when that 25 popped up, I was like, what the heck? What the heck? P hat minus P naught. I am prone to error. I am error. Minus. Oh, thank you, Kayla, right there. Double check my work. I appreciate it. I will make errors, especially after last question. I've lost everyone's trust in my ability to solve these questions. Someone was watching that video and they were solving along with us and they might have made the same error. And then and they're like, what the heck? Why do I watch this guy? This guy can't even solve these questions. Does he even know how to do this? Does he? I lost trust in my PI calculations. Does he know? That's the meanest thing a student ever said to me was in one of my first years of teaching, I got a little, you're solving a lot of questions, so your brain can sometimes make an error like we have. And a student looked at me and they said, do you even know how to solve this? And I was like, yes, I do. I'll swear I do. So it's just easy, to make errors. We all make them. And there's the Z-score. I know that's the meanest thing a student's ever said. Do you even know how to solve this? So that stung. Little did they know when they said that I'd be remembering it a decade later. So solving the same problems. That do I even know how to solve them? Apparently not. So there's the Z-score right there. The Z-score is negative 1.31. This p-value is guessable, but it's pretty tough. We're doing a does not equals, a does not equals, a does not equals. So the does not equals is going to look like the following. So we go right here, we go down, down, up, up, and we landed at negative 1.31. And we go to positive 1.31. And this p-value on this one is going to be somewhere around 18%. I'm going to guess right here a p-value of 0.181. That's a guess. And everything's wrong with the numbers on the question on the chapter 15 quiz. And then we'll do I think we're going to do some write-out nulls and alternatives to end off stars today. Can you let me know, Catherine, which ones you're talking about? You might have to email me, Catherine. I'll take a look. Yeah, we'll do some rights and nulls alternatives here next. We're going to put this into the David M. Lane. There's the z-score. There's my guess. That's a guess. This is, are the twin birth rates the same or are they different? How close are we at our guessing today? Our guesses are, we were close. It's 19. Oh, wait, so did you, I think Kayla, Kayla, you got me. I was like, wow, Kayla. So Kayla, I think, you rounded up, right? It wants us to round up. So I think Kayla rounded up, which it wants us to do. And Kayla's like, here's my guess. So 19.02 is Kayla's guess. Kayla, your guess is closer. I was off by 1%. So good guess there, Kayla. Kayla guesses 19.02 on the dot. That's worth 100 points right there. Great work, Kayla. So 19.02. So are the conditions met? Yes. We were testing to see if they are the same or if they are different. The z-score was what we calculated right here. The p-value, Kayla, just decimal place or accurate guess right there. It's 19%. It's 19.02, but rounds. And then this is a high p-value, so we fail to reject the null. The proportion of twin births for teenage mothers is not different. We do not reject the null. We're getting everything right. What is going on? What is going on? We do not reject the null. Don't tell me we're using some crazy alpha. 3 decimal places. Rounded 2 decimal places. Wait, rounded 3? Wait, is it seriously? Wait, what? Wait, what? I think my brain's fried, everybody. What's going on? That would be a very, very extreme z-score. Kayla, what's going on? Kayla, help me out. My brain broke. Do I even know how to solve this? My gosh. When it rains, it pours. Round to 3 decimal places. So is it not? Let's just check to see if it is this one. That's wrong. Yeah, so it is the p-value. What's going on right here? Okay, wait. We're doing the does not equals test. We got a z-score of, did I not put in the right z-score? Oh, my Pearson, what are you doing? Does it really want me to put in the z-score without rounding? I'm about to write a mad email to my Pearson. I am about to write an email to my Pearson about this. This is on my Pearson. Yeah, that's... What is going on? Okay, I've seen this. I've seen an error before where it does this. Oh, that's... Whoa, whoa, whoa. So it's not the p-value. It's not the p-value. Oh, I'm sorry, everybody. My brain is fried. Was it the z-score because it rounds down for some reason? Let's change the z-score drastically. Wait. So I think it's saying the z-score. Do you see it? Rock, talk to us, man.
It doesn't matter.
We're doing the two-sided alternative. It doesn't matter. It doesn't matter. It doesn't matter. Rock knows the answer to this. It doesn't matter. Everything we had was correct. Sorry, I'm going too quickly. The thing is it's the two-sided alternative, so it doesn't matter. The z, we use the absolute value of the z. Just gonna get every question wrong. I'm just seeing if you're catching every mistake I do. Trying to throw out many mistakes. Went all morning, all day, all yesterday, all the end of last week. No errors. No errors. Let's go right. I know. I was like, what's wrong right here? Okay, let's write some nulls and alternatives. Great way to end right here. Let's see. Do I even know stats? I don't know. Kayla, I don't know if I know stats anymore. I lost all my confidence. Let's write some nulls and alternatives. Let's see if we know how to do those. Here we go. Ending off the office hours today, writing some nulls and alternatives. Oh my gosh. I think it's the bright lights. That was not good. Joke's over. Shouldn't do that. I knocked over a camera thing. It's fine. Let's do this. Now I can... Yeah. Okay. Let me not detach wires. Don't touch things, Brian. Let me put my picture back up. We'll fix the camera that I knocked over after class. Everything's breaking down. Okay, here we go. A dictator is concerned about their negatives. Well, they're a dictator. I don't know why they're concerned about that. I mean, whatever. Don't be a dictator. So the null has the what? The easiest thing we can do here for these is the null has the what. We should know null has the what. Null hypothesis has the what. You see the null hypothesis, you know each time it's going to have this. You know the null hypothesis is going to have the what's. You know it. The null hypothesis is going to have what? Every time you see the null, you're like, has this. I know the null hypothesis is got this sign every time, which is going to answer this question, and this question right here. All the nulls have all the equal signs. Now we have to look for the evidence-based claim, which is the alternative. And so we're going to ask, they want to keep their negatives below 72%. So we're going to say that it has to be less than 72%. Is a coin fair? Well, either the coin is fair or a coin is not fair. Only about 17% of the population will try to save their troubled marriages. Oh, God. Try to save their troubled marriages, succeed. A seller of motivational tapes claims that listening to the recorded messages can help people succeed. So we want people to save their marriages. So they're trying to save marriages. Amazing topics, right? And so they'd want more people to say, I know, geez. Oh, geez. So they'd want the proportion of people who save their marriages to be greater when they listen to the motivational tape. So great stuff right there. Good practice on writing nulls and alternatives. Same thing going on right here. We would have the null as the equal sign. So the null has the equal sign. Anytime you see the null, it has the equal sign. Just nice and easy. Now you have to ask yourself, are we doing categorical or quantitative data? These are people graduating from high school. So that's categorical. So it's P. These are cars that need transmission work. So that would be P, not P hat, not P hat. It's P, the true proportion. We field test a new soft drink. So we're seeing if people like the new soft drink more. So it's, do you like the soft drink more? That's P. The other one here is mu. These are the only two options right now. P is for true proportion. Mu is for true mean. So we'd be doing P right here, which is the true mean. Now we need to go over here and we need to do a test. And all these are going to be true proportion. Whatever you select for that is right here. So good practice. And there we go. And now we need the sign of the alternative. Has this changed? Changed is the key word, and we'd say it does not equals. The manufacturer hopes that a redesign will stop the transmission problems, so they want the transmission problems to go down. And last but not least, we want to see planning to market if only we are sure that over 60%. Remember, this is the evidence-based claim right here. So that's got it. I'm going to have to pick up the camera I dropped. There we go. 2 problems fixed. Oh man, so easy to make mistakes, but we won't make those mistakes. With that, Puppet Shark, is it time to prepare for class? I think he's going to say his famous line. Yeah. It is. With that, everybody, we'll be back here. We'll be back streaming some more tomorrow, but great work, everybody. Don't make mistakes like Brian. Don't be like Brian. Get those questions right. Practice up. Little mistakes. Easy errors to make. You got this, so talk to everyone later. Bye for now. Bye. 15 minutes till class.